Okay, welcome to this video on covalent bonding. You will want your guided notes in front of you so you can write down the things and fill in the blanks from this PowerPoint slide. We will kind of review these notes on Monday, and what you should try to do is do the assignment that I gave you as well, so you kind of have a head start on your homework for next week. And then also I will include a few questions about this video on your polyatomic ion quiz, and again that quiz will be over the first 5 on the list that you see, starting with ammonium and then the next 4 polyatomics after that. So that'll be Monday, and then after that we will get to some practicing with these compounds and covalent compounds and drawing some pictures and doing all that good stuff, so we can get some extra practice. But your goal is to make sure you have your notes filled in so you're ready to go for Monday. So let's go ahead and start talking about covalent bonds. Covalent bonds, the first thing you want to remember is that they're very, very different from ionic bonds. And typically the way we can tell that in a lab setting is typically by their properties. So a lot of times covalent bonds, because of the way the bonding works, they have very, very different properties. Ionic bonds are very strong because we've given up an electron or we've gained electrons to acquire a charge on our atom, which is a cation or an anion. These charges allow the atoms to attract to each other. Covalent bonding doesn't quite work that way, and that results in a weaker bond. And so as a result of that, we typically have really low melting points for those compounds. So for example, sodium chloride is an ionic compound, and it has a melting point of 1474 degrees, which is pretty hot. You can't melt that on the stove or anything like that. But thankfully for us and anybody who likes to bake, sugar is a covalent compound and melts significantly lower, and we can use that to bake and make lots of good stuff. So that's one of the key points as far as the properties go. That's very, very different. Another difference is that covalent compounds typically don't conduct an electric current when you melt them or dissolve them. You may in some cases have a very, very weak conductivity as far as the electric current goes, but not nearly as strong as the ionic bonds if you have anything at all. It's kind of a result of when you dissolve or melt and break apart those covalent compounds, there isn't enough charge there. With ionic compounds, we've given up electrons to create a charge, and when we pull those structures back apart, we're left with those charged particles, and that's why we can conduct the electricity. But that's not the case with covalent compounds, because we're taking and putting together 2 different nonmetals in a different way than we do for ionic compounds. So let's take a look at what a covalent bond actually is. A covalent bond is essentially 2 atoms that really both want electrons. They want to gain them, so they basically make a pact and decide that they're going to share their electrons. You don't transfer any, nobody loses any, nobody gains any strictly. They simply share them. So at one point, each atom will have those electrons equally. So this diagram over here kind of shows you the sharing of electrons. So in the covalent bonding's case, hydrogen will always act as a nonmetal, meaning it will always pick up an electron. Hydrogen can swing either way as far as gaining or losing electrons, but in covalent bonding it will always gain them. So it will act as a nonmetal. So here we've got carbon and hydrogen. They literally share these 2 electrons. So carbon gets its 4 and it has an octet, and hydrogen follows the duet rule, meaning it's going to have 2 valence electrons. So they get this partnership going on where they can share their stuff. And typically elements with the same electronegativity or elements that are then close to each other on the periodic table like to form these bonds, because they like to work together and they say, hey, I want some electrons, you want some electrons, let's make a deal. So they essentially share that space. So everybody's got an octet. Now, since they're sharing those electrons and not transferring them, the bonds are much weaker. So a lot of our molecules that we have are made from covalent bonds, and that's actually the definition. Two or more elements that bond covalently. That's a molecule. So ionic compounds are not molecules. So let's take a look, compare and contrast here. Here's what we know about an ionic bond. We get something positive and something negative. But that's not the case in a covalent bond because we are sharing those electrons. We're not losing any or gaining any. So if you take a look here at this bottom picture on both bond types, you can see that we're sharing these two dots, whereas over here this positive ion is left with no valence electrons and the other guy has picked those up. There's no sharing going on. This guy is holding on to his valence electrons. He got rid of his and doesn't want them back. Here it's an equal partnership. So here's kind of what it looks like on a hypothetical scale, because we can't exactly tell where those electrons are. So it's kind of a region in between. Here is where the bond would be and where that sharing is going on. And this is between two fluorine atoms, which is a bit different than what we've seen before. So in covalent bonds, we can actually get the same element bonding to itself, so it can essentially make itself happy and give itself some electron. So let's take a look at some of these compounds. Let's decide what's ionic and what's covalent. So ionic compounds, you always have a metal and a non-metal. So if we look at the ones that I've listed here, here's aluminum, which is a metal, and here's oxygen, which is a non-metal. And this is one we've actually diagrammed in the notes as far as how the electrons transfer. And so this would be ionic, the first one here, aluminum oxide. Then we have CH4, and that's going to be carbon's a nonmetal, and hydrogen will then act like a nonmetal. So this would be covalent. Ammonium, or ammonia, here is actually also covalent because you have hydrogen, and the way it bonds with nitrogen, it will act as a nonmetal. Water, we know, is not ionic. You have hydrogen acting as a nonmetal, and then you have another nonmetal, which is oxygen. So this should be covalent. Now, on this one, you need to be careful. Okay, if you remember your polyatomic ions, and I do believe I have a slight typo here. In the formula, there should be two of these ammonium groups. Sorry about that. We have ammonium and we have sulfate. These are both polyatomic ions. Yes, there's some covalent bonding going on with the nitrogen and the hydrogen here, and the sulfur and the oxygen, but overall, these have charges. And so when they attract, they're attracting based on those charges, which makes this ionic. Okay, so typical ionic compounds, where do you see this stuff? Well, you use it every day. Obviously, we all drink water. Water is a covalently bonded thing. If you use hand sanitizer, alcohols in the hand sanitizer are covalently bonded. Propane or butane lighters, that's propane and butane are all covalently bonded things. And if you clean with ammonia at all, that's also a covalently bonded thing. So let's talk about how they form. Basically what happens is when you share electrons, you're going to have to reach a point of that's called maximum attraction. So essentially there's some attraction forces going on, but there's also some repelling forces. So two atoms come together and essentially their electrons are repelling each other because they both have negative charges. But eventually they move close enough and the attraction forces between the protons in the center of each of those atoms starts to outweigh the repelling forces. So essentially you get one atom's electrons being attracted to the other atom's protons. So the protons are positive, the electrons are still negative, and we know opposites attract, so it works out. So here's a picture of that. Basically you've got repulsion or repelling forces between the electron areas, and then but you've also got attractive forces going on, and when these reach kind of a state of equilibrium, or kind of the maximum spot, or the maximum attracting point, that's when we get the bond. Now, you're not making any one of those atoms an ion by gaining or losing electrons. You're just essentially pushing stuff out of the way enough so you can get an attraction between the plus in the middle of one and the electrons of the other guy. So definitely not as strong. So there's some elements that naturally bond covalently. So all of these atoms tend to share their electrons with themselves, and they're much more stable than that in nature, and that's typically how we find them. So these are called diatomic, and you'll want to kind of memorize these. These are the ones that you'll see on lots of probably tests and stuff. Not just in my class, but overall standardized tests and stuff. These are the ones they'll bond with themselves. So basically, oxygen will come up to another oxygen and say, "Hey, I need 2 electrons. You need 2 electrons. Let's just share our pairs of electrons and give ourselves a full shell." And it's much more stable for them to exist that way. Not very strong bonds, but they are more stable. So what we end up getting with covalent bonding is essentially different types of bonds. So I can have a single bond, and each bond will represent 2 shared electrons. So you can kind of think of 2 electrons rotating between both atoms. So one line that you see is 2 electrons. Sometimes I can get 4 electrons being shared. So that's indicated by a double bond, or 2 pairs of electrons. So oxygen, which is diatomic, will share 2 electrons and then 2 more because they each need 2 for their outer shell to satisfy an octet. A triple bond then shares 3 pairs of electrons, so 6 altogether. So nitrogen will bond with itself in 3 different spots because it has, it's in group 5, so it has to get 3 more electrons to get to an octet. So these are the 3 types of bonds. As a result of covalent bonding, basically what happens is a bunch of overlapping between the orbitals. And when we get that, we call those types of overlaps a sigma bond, which is a single bond, and then we also have a pi bond, which is a different type of overlap. So you just want to remember basically every single covalent compound is going to have a sigma bond because everybody at least has 1 bond somewhere. If you have a double bond, that's where you introduce the pi bond, and that's a different type of overlap. So you get 1 sigma, 1 pi. A triple bond is 3 bonds, so you have at least 1 sigma bond and 2 pi bonds. It's, again, just some of the overlapping. You'll just want to remember everything's got a sigma bond. When you got more than that, 1 or 2 of those other bonds is a pi bond. So let's take a look at this compound, and this is a structure we'll practice drawing on Monday, but if I wanted to identify sigma and pi bonds, obviously every single single bond here between the hydrogens and the carbon, that's a single bond, those will be sigma bonds. Okay, and then here in the middle I have a double bond. So a double bond has 1 sigma overlap and then 1 pi overlap. So anything that's single is sigma, anything that's double or triple will have 1 sigma and the rest will be pi's. Alright, so the last thing you want to know about bonds. When we talked about ionic compounds, we talked about lattice energy to break those up. When we have covalent bonds, we talk about bond dissociation energy, which is essentially the energy just needed to break that bond. Now, the more bonds you have, or the more electrons you're sharing, the shorter the bond length. And the shorter the length, the closer you are, thus you have a stronger hold. So it will take more energy to break you. So if you have a double bond and a triple bond, the triple bond would be much stronger, shorter, but would be much stronger than the double bond. So if we take a look here, we have for length, you just want to remember, most importantly, you have a single bond is the biggest, double bond is next, triple bond is the shortest. So on Monday we will practice drawing out some of these compounds. Those are called Lewis structures. So most importantly, make sure you have the handout, the notes filled out. If you need to go back and watch some things or rewind, that's fine. And then make sure you try to answer some of those questions on the homework sheet. And then be prepared for your polyatomic quiz on Monday, as well as a few questions that will be added about this video. Have a great weekend and good luck, deer hunters.